Good afternoon, everyone. It's a pleasure to welcome Professor Hong Guo, who's the James McGill Professor of Physics at McGill University, who will be our main seminar speaker today. Professor Guo was born in Shenyang, the capital of Liaoning province, which is in fact the largest city, I think, in northeast China. Right?
Manchuria.
I've been to Shenyang also.
Yeah.
And he was also a graduate at Sichuan Normal University, intending initially to be a high school teacher. But in 1981, after passing a key national exam, he became a graduate student at the University of Pittsburgh, and he obtained his PhD under Professor David Jasno. He was a postdoc with Professor Jim Gunton at Temple University and with Martin Grant at McGill. And he joined the physics department as I think an assistant professor at McGill in 1990. So his research concentrates on two main areas. First of all, electronic transport theory in mesoscopic and nanoscopic systems, and the physics of nanomaterials. And secondly, well, actually, in that area, nanoelectronics, he has done pioneering work on the development of theoretical formalism and computational tools for application to nanoscale electronic devices. He has combined non-equilibrium Green's function formalism with density functional self-consistent field theory, DFT, to analyze and predict non-equilibrium quantum transport properties of nanostructures from first principles. Professor Guo has won a number of prestigious awards, including the Killam Research Fellowship in 2004-2006, the Brockhouse Medal of the Canadian Association of Physicists for outstanding experimental and theoretical contributions to condensed matter and materials physics, and the CAP, the same Canadian Association of Physicists, CRM Prize, that's the Centre de Recherche Mathématique in Montreal, the CRM Prize for Theoretical and Mathematical Physics in 2009. In 2004, he was elected a Fellow of the American Physical Society, and in 2007, he became a Fellow of the Royal Society of Canada. So please welcome Professor Hong Guo for his seminar, Device Modeling from Atomistic First Principles.
Thanks, Arthur. Thank you for coming today. And it's very kind that when I was a assistant professor, I know Arthur's name, our very distinguished scientific leader of the country, and it's really my pleasure to be here. So I want to tell you a little about the work that we have been working on for a long time, but I will focus on some new development of the last few years, which allowed us to reach to a sort of a milestone time, sort of a stage where I believe that we can be useful, okay, in device simulation. So I will give you a very quick introduction why anybody wants to do this, and then I will focus on four critical problems that brought our theoretical technique to a stage where I think we can solve some engineering problems. And then I'll give you a little example and summary. So basically, the idea is can we calculate quantum transport properties from atomic point of view? So I want to simulate a device starting from atoms, so without any parameters. Okay. Of course, in the end, maybe you will, in the future or something, you can survive with a few parameters, but we don't want to use a continuum model because of certain issues I will explain. So when I was a postdoc, actually I worked on this kind of problems, that an electronic device is a continuum of material, and then you solve some method, using some method of solid-state physics, like effective mass or K dot P and so on. And then the material properties are coded into certain parameters. So since I went to McGill, I always wanted to see whether we can solve physics problems so that will enable us to do these kind of things. I should have found all the pictures, but I want to show these four I just dug out from some journal. And my key two theoretical postdocs before, and my student Jesse Masson, who is now doing a postdoc in Purdue in electric engineering. Fedos is in Hong Kong on faculty, and many other people I will thank when time comes. So basically, the question is that can you calculate a transistor? from first principles. Okay, so this is a very, of course, useful problem to do for solid-state physics, people like us. But actually, it's a very hard problem. And the reason is that not only we have to worry about a lot of physics, just the sheer size of this chunk of metal, of this semiconductor is a lot of atoms. So you have to solve a large number of atoms. In solid-state physics, we solve materials with a few hundred atoms to 1,000 atoms, so using a theory called density function theory. And this is a ground state theory, which gives you ground state energy and so on. Usually, solving 1,000 atoms is something that you can be proud of or something like that. But this is much more than this. Not only that, in order to solve a semiconductor device, you have to learn how to dope this device with impurities, and then that will induce, impurity scattering, and then which give you randomness. Therefore, you have to learn how to average the result and then analyze this average. And you have to get the band gap correctly. And we know that this theory, while it's very useful, has a problem of predicting band gaps of semiconductors. So we can use very high-level theory, which give you extremely accurate band gaps. But this theory, you can use on 50 atoms or so, and not these big systems. And then you have to look at large systems, and most important thing is how do you know your theory is correct? Okay, you have to somehow benchmark it. And on a lesser extent, we have some physics issues, electron phonon scattering, these other things, and we have to worry about. So this is actually a very complicated problem. So one could ask, why would anybody want to do this? Okay, and then so in electrical engineering, this is sort of a TCAD type simulation of a transistor that you parameterize your transistor by many parameter currents for a given voltage on different contacts. And then you write down a sort of a compact model where you parameterize your current in terms of many, many parameters. Okay, so this is done for the last many, many years and has been extremely successful. But you really have difficulties to go on. This is, we all know Moore's law of transistors, but there is accompanying another Moore's law of fitting parameters, actually. This is for device simulation. And as your feature goes more, your number of parameters is also increasing. So if you look at this graph from my engineering friend, and that he showed me this graph, which says our device models in engineering uses 1,000 parameters, for example, or hundreds of parameters at least to simulate a transistor. So Mong-Song, very good friend. I mean, he is the code manager of BSIM4, for example. And this is an issue that you want to work on new materials, then you have to fit the parameters. And that is becoming very expensive and time-consuming. And it would be very nice if you can predict everything. Okay, so and we have a lot of materials in nanotechnology. And I just compiled a little picture, topological insulators, graphene, and things like that. So in this talk, I will try to convince you that it is probably possible to calculate everything from first principles. All right, so here is our research goal, is to produce atomistic TCAD. Okay, technology, computer-aided design, it's atomistic. So I come from this side of science, and we work very closely with engineers and trying to close this science engineering gap to solve these new problems of new materials, emerging ideas, and so on. And right now we use quantum chemistry, quantum physics, and so on, material science, and you can solve small problems. Okay, and then can you really enter this regime is our goal. Okay, so to do such simulations, I will first consider some physics. Okay, there are two pieces of physics that I think is absolutely important. The number one is that we have to realize when you have an electric current flow, it is already a non-equilibrium problem because you have particles flowing into the system. So this is a non-equilibrium problem intrinsically. Okay, and therefore you have to worry about non-equilibrium statistical mechanics. Engineers has solved this IT problem for us without any harmonic, right? They solve Boltzmann equation, which solves statistics. So in quantum transport, you also have to do that. You have to solve quantum statistical distribution. So this is a very important issue that we in physics usually do not appreciate that much, because we spend all our life constructing extremely accurate Hamiltonian. But for transport, this is another consideration. So by far, I think the very important thing is to worry about your density matrix, your statistical distribution under the current flow conditions. And then we have to have a good Hamiltonian. And in this case, Hamiltonian gives us energy levels. And then I will fill the energy level by my statistics. Then I can have a reasonable theory. Okay. So in a device simulation, what we do is that we divide this system by a scattering region plus left and right electrodes. And that's my Hamiltonian. So we have to calculate the Hamiltonian. And we have to have a self-consistent theory. So to deal with this non-equilibrium statistical mechanics, there are, I know, of two sort of popular methods. One of them is to use this NEGF, this non-equilibrium Green's function theory, which actually calculates the non-equilibrium density matrix. And this is useful, and that's what I am familiar with when I was, my training and so on. So that's what I use. In quantum chemistry, people actually also do very, large calculations by evolving a non-equilibrium density matrix from some initial equilibrium state, and you can iterate this time-dependent density matrix. So that's another possibility. Okay. So and then next is what Hamiltonian you want to use. As I mentioned that early on, we use effective mass and so on. But there are many, many different Hamiltonians you can use. Okay, so in this work that we have been doing, we choose density function theory, which is sort of sitting in the middle of this spectra. And but in the end, it doesn't matter what Hamiltonian you use. You have to compare with measurements and with industry database. So this is the main theoretical consideration. So from our point of view, from this theoretical background of mine, that I am familiar with this kind of thing plus non-equilibrium Green's functions. So after many years, so in 2001, this is the we have finally figured out how to do this non-equilibrium Green's function based, material theory, okay, density function theory. So in this case, the basic idea is that I use some kind of self-consistent field theory, DFT. I should put this DFT in quotes, okay, and that calculates the Hamiltonian of the system. And from the Hamiltonian, I can calculate my non-equilibrium Green's function, which tells me the statistical information, and then that will give me the density matrix. So I iterate this until I converge. So essentially, this is the basic idea. Many people don't use DFT to do this. You can use effective mass, you can use tight binding, and we did those things before as well. But DFT seemed to be sort of a material theory of my choice, so we do it. So the important thing is that we construct density matrix by some non-equilibrium Green's function. So this equation actually tells me how do you feel your energy levels at non-equilibrium. So that is the physics that behind this. And then we have to realize that this DFT is not really the ground state DFT anymore, because the Hamiltonian matrix, okay, is constructed by some density function theory, looking theory, but the density matrix entering this DFT is constructed at non-equilibrium. So this is not a ground state theory, and there is no variational principle. So that's why this theory, when you do calculations, it becomes much more difficult to converge mathematically, and there is no iterative techniques as far as I know so far. We tried many times, we couldn't get it. So it's really because of the non-equilibrium physics. But other than this, you can just make a theory. And so in 2001, my student, Jeremy Taylor, of course, he moved on to start up companies, sell software and so on, and to become a very prolific entrepreneur and so on. But he figured out some of the key development in this formalism. All right, so now we want to bring this formalism to a stage where I can simulate a transistor. So the first problem we want to solve is how do you dope the system? And how do you solve the time-dependent, not time-dependent, how do you solve the disorder scattering problem? Okay, so this one I want to thank another PhD student of mine who did a PhD thesis on this. He is in Princeton right now doing a postdoc. And so essentially, the issue is doping and disorder scattering from atomic principles. So in semiconductors, if you heavily dope, we're talking about 10 to the 18th or something. So we're talking about one atom in 10,000. And so if you want to do brute force, disorder calculation, you have to simulate 10,000 atoms by putting in one impurity. Obviously, for atomic calculation, this is just impossible to do. Okay, and not only that, your impurity can sit in 10,000 locations. That kills you also. So you cannot really do that. All right. So we have to develop theory, so that we can look at this problem and Yuki's work. I think many of the theoretical issue was only figured out this year. So we have a technique paper saying all the theoretical formalism theorems that we prove. So this is the issue that you have a few impurities in a big matrix of host material. And usually in physics, what we do is that we generate many configurations and compute each and average it. And this is not practical. So we don't do it. If we don't do it, you calculate conductance as a function of sample. You find that it depends on which sample you calculate. It fluctuates like crazy. Okay, so we know this, that we have to do many samples and average it, and we cannot do that. So the issue is that can you derive an averaged formula? Okay, and then you calculate once. So that's basically the theoretical advance that we are doing. So what we do is we use a physics technique called coherent potential approximation, CPA. So in this theory, you have some dopant, okay, it's a statistical analysis. So you have some impurity sitting on some lattice side. Let's say you have X% of impurity. So this theory builds an effective medium which says, on each side I look at it, it has X% to be nitrogen and 1 minus X% to be silicon or something. So you build some kind of mean field, effective medium theory that allows you to actually do average analytically. Okay, so that's very useful, which has been developed in the 60s. It's a very famous, Solvent and these people developed this. So we know this theory. Okay, it's just not used for device modeling, and it's done at the equilibrium. So if you want to look at transmission coefficient as a function of the scattering, you have Green's forward propagating, Green's function and backwards. And when you average over impurity, you have to average over this. And that was even done actually in the 60s. So in the old theory, you have these techniques. But what was not done is how do you do it at all of that at non-equilibrium. So that waited until Yuki to figure this out. Okay. So basically what we have to do is to average the density matrix that will average, give us the impurity average density matrix. Once we have that, we can solve this again, and then we will get transmission coefficient and so on. So in this paper, he developed his theory, and that works. So we have a method to do this non-equilibrium. Okay, so that's the thing. And so this is the progress that we made. Of course, 5 years ago, we had a lot of theorems. We couldn't prove it at the time, and we only prove it numerically, to 16 digit, it works. So we said it has to be right. But only until this year, we were able to finally prove many of these theorems analytically. So we know that this is a very solid piece of work. So the essential idea is that if you want to do this average, you have a forward propagating Green's function and backward Green's function. And when you average it, you can break this average into the average of the Green's function itself, multiply by some self-energy, and this is called vertex correction. So essentially, how do you evaluate this vertex was the theoretical problem you have to solve. And we solved it, and then you can do this. Okay, so as I said, that of all of this theory, only until this year, 2013, that we were able to completely understood all the issues. But anyway, the conclusion is that this problem is solved by this non-equilibrium coherent potential theory that we finally was able to work out. And so after solving this disorder scattering, now we know how to dope the semiconductor. The next problem, of course, is a very big problem, is how do you get the band gap right? Okay, in order to simulate a semiconductor, you have to do this. And so our experimental people like the Chen, they measure the band gap. So they tell us you are completely wrong. And so we have to do it right. And this turns out to be a hugely difficult problem. So again, solid state physics people make progress in this. So we have density function theory. And then density function theory is about approximate theory. So it's not everything is right. Okay, one of the things which is completely wrong was the band gaps. So if you use some functional called local density approximation, which is part of the approximation you use for density function theory, you will get a band gap which is half of the experimental band gap, so to speak. So this is a well-known problem. If you do very high-level theory, like this kind of theories, okay, exact exchange and so on, you get reasonable result, but these are very big calculations and you can only do 50 atoms. So I think that that was the problem, and then we were stuck. So we were developing some things here and there randomly, and I was completely depressed for a while, and suddenly, 2009. Okay, this European group, Peter Blaha, he found, okay, by adapting a quantum chemistry technique, this Becky-Johnson potential, and BJ, okay, and actually both of them, Becky is in Canada, right? Quantum chemist, very well-known quantum chemists. They have some functional, and these people modified it, so this MBJ, okay. And what they found is that if you do that, somehow you can get very good gaps for many compounds. And the calculation speed is as big, as fast as LDA. So this is very good. This is not a fundamental physics, okay, solution, but it's a practical solution to this band gap issue. The reason is that they use something called semi-local exchange. Local exchange is wrong. Completely non-local exchange is good, but can do small systems. So they made it something in the middle, and then make it sort of work. Okay, so essentially they solved some issues about the discontinuity of your exchange correlation energy and so on, and made sure that this works. So when I saw this paper, I said, that's the saver for our research, and we implement right away this method. Of course, we have to implement into our software of device simulation and so on, but that's just, these guys already figured out this. So we just did it, and so now I can tell the CHME that, your experiment data or theory data, they agree, so it's very nice. We can get it right. And so this is a very important progress, I think, from a calculation point of view. You can really get it. So we can calculate, this year we calculate all the zinc blende 3,5s, and then you can see that our calculated band gaps, band structure, the red line, and then compare with this experimental data, they are just right on almost for many compounds. Okay, so this message is that this modified, Becky-Johnson potential, if you work at it, okay, you can make it to work for at least 3,5s. It works for silicon and many other systems. We calculated about 30 compounds, and it works very nicely. It does not always work. So if you want to work on, copper oxide or something, it will give you something wrong. Okay, so this is not a first principle theory, but for semiconductor physics, this works. So we can use it for many device simulations if you know what you're doing. Okay, so this is not only that, it works on, we can calculate the band alignment between gallium arsenide and aluminum gallium arsenide. And I told you that we learned how to dope this. So we can calculate the band alignment as a function of doping concentration. And this is something that I knew that I wanted to know when I was even a postdoc, a long time ago. It was never solved. So you see that the band gap of aluminum gallium arsenide as a function of X, it changes from direct band gap at 38% to indirect band gap. And all of this agreed perfectly with experimental measurements. So the first time that we can calculate the entire band alignment. Okay, so for semiconductors, this works nicely. We are testing on Schottky barrier metal, semiconductor interface. That is harder to do, but at least that this is progress from band gap point of view. So the next thing is to solve large systems, and this is something that we have not really made very big progress. So essentially, this is done by mainly my PhD student, Vincent. He has a math degree. He's an extremely good graduate student. So to calculate the Green's functions, as I told you that we are using non-equilibrium Green's functions, so you have to invert some big matrix. So how big? Okay, this matrix, suppose you have a silicon of 8 nanometer square times 40 nanometer long, some transistor channel, and the matrix is a milli sort of square. Okay, you have to invert it. And then this is not totally sparse. Okay, it's reasonably sparse, but it still have atomic orbital goes to several neighbors. And this just is a very tough problem. And then you cannot iteratively solve because this matrix is not positive definite. It has a complex potential in there. So you have to really directly solve it. So this is a very difficult problem. And so in physics, you hear in quantum chemistry, there are something called the order n technique to solve material systems. But the order n technique is based on locality. Your density matrix is local. Okay, so if a density matrix of R and R prime, it decays if R and R prime goes large. So in this case, because of this property, you can actually, divide your big system into small chunks and calculate each chunk on each computer or something. Then you can actually do big systems. So for equilibrium, all of these order-n techniques is based on this principle. But for non-equilibrium, we don't have this principle. Unfortunately, density matrix is not local. Okay, so for non-equilibrium density, we have part which is locality. The other part is non-local, so you are dead. So all of this order-n technique is out of the window for non-equilibrium problem, unfortunately, so far. And so what we have done is we went through all the algorithms of mathematics, trying to find one and so on. But anyway, so at this moment, we found our own method, and which works up to about 20,000 atoms. Okay, so we were able to do 20,000 atoms for a self-consistent step around 15 minutes or something. And so this is a painful calculation, but at least you can do big systems with the memory limited by 3G per core. Okay, so we can do a large, massive parallel computation with 160 core and then do something like this. Okay, so this is the largest that we have reached for DFT calculation. So for a device simulation, the largest we have done is about 20,000 atomics. This is for silicon, and 10 orbital per silicon, and then we can converge this result in about several days. So we are now working very hard to reduce the computation and try to see whether we can really make this a easier used engineering research tool. So because of this problem that we can never go to 1 million atoms, we also developed certain tools to generate tight binding parameters. And with tight binding parameter, you save this self-consistent loop, and then you can do much larger systems. So we can solve 1 million atoms within a day or something like that, 2 days. Or now actually it's a day. We can solve this transport problem of a structure with 1 million atoms, 10 orbitals per atom, non-self-consistently. So this is some kind of progress. All right, so this brings me to the last critical issue that I want to solve is all this correct or not? Okay, so benchmarking. Okay, so this one I have to talk to an engineering friend, and they use something called Centaurus. Okay, so this is a drift diffusion, many parameters, but it's very accurate. It seems to be for silicon at least. So then we calculate ours and then we compare with them. So basically, Centaurus is a synopsis software, and I have some student who work on synopsis. So they said, oh, you have to run synopsis to compare. And then I look at it, they charge you a lot of money, so I didn't pay. So I asked some friends to run this. And so in this Centaurus, they have a device simulator. It's a drift diffusion with solving Poisson and so on. And it has 1,000 pages of parameters that they describe. Okay, so this is, but for silicon, it's very accurate. Okay, so they have a lot of silicon parameters. So if you look at their manual, I studied this manual. I found it has many chapters. If you say that you want to do Poisson equation, what happens? Okay, in Poisson equation, you solve this equation. In this equation, you have many parameters, and then you go to another page and you study them. Okay, so basically, it's a tool from industry. It can simulate silicon transistor, and my student who works in this company thinks this software is correct. Okay, so let's use it. Okay, and so what we do is that we use this, our tool, okay, everything from first principle with no parameters, and then we do a 10 nanometer, actually we do 11, 16 and something, silicon channel with this atomic self-consistent method, and then we use Centaurus to do this. Centaurus is like that, okay, so you simulate. All right, so we did a TFET. Okay, so this is a potential. We calculate potential at equilibrium, at non-equilibrium, and then you 300 Kelvin, and it's a silicon, PIN structure. Okay, so it has. This one is not very large. Actually, it has maybe 800 atoms or something in this region, and but nevertheless, that if you put two curves together, they are quite reasonable. They agree. There is no adjust parameters in our calculation. We send these curves to them. And then you see that at non-equilibrium, we differ a little bit. And then we found that in Centaurus, they use something called floating boundary condition to solve Poisson equation. And we use fixed boundary condition. And that was the little difference. And I believe fixed boundary condition is more physical, actually. And then we do a MOSFET. So this is the potential. We calculate the PNP, NPN. And then we dope real atoms. This one we dope real boron atoms into our silicon. This we dope real atoms, phosphorus. And then after that doping, 2 different concentrations of doping using this CPA method. And we calculate potential. You see that these 2 agrees quite well. Okay, there are some difference, but this is basically good enough, I think. And so basically we can compare with, we did some other systems and so on. I have to say I'm quite proud that every time we found disagreement, it was always Centaurus problem, it seems. Okay, so this one, we finally were able to publish it to show that this atomic simulation had reached a stage where you can actually make quantitative comparisons. Okay, so this is the first time I think I have reached this far from atomic first principles. So, so now I have told you that to summarize, by solving these various, 4 very tough problems within the last, I would say, 10 years or so, that we finally reached in 2013, that we can simulate silicon devices. This paper is about some strain effect. You can get all this perfect agreement. And so these are the 4. And of course, along the way, we have other physics. You have to add, electron phonon scattering, for magnetism, electron magnons, spin optophysics. And I have some students who are interested in optical properties, so they added photons. And I'm, as a physicist, I'm interested sometimes in some correlation effects and so on. So we have some other things added to the tool. But I think these 4 are most important, which brings us to a stage where I can say something to real systems. Okay, so let's take some examples. So the first example I will give you is done by a PhD student, WSe. He is now doing a postdoc at Purdue. And so we were looking at a MOSFET. You have leakage, right? Leakage current goes to the dielectrics through the gate. But that is sort of relieved a little bit by using the high K material. And there is a source to drain leakage, which seems to be more difficult to do. So the reason is that when this L is very short, you just have tunneling. So you cannot turn off the transistor. It's over. The electron just goes through, tunnels through this. And so can you do something? Can we say something about this problem? And so WSe had the idea that the reason that you tunnel through is because your potential is not high enough. Okay, and so that is easier to tunnel. But you can only dope so many impurities to build this potential. So therefore, you cannot do very much over there. But what he's thinking is that maybe we can dope the same amount of impurity, but only dope it in some kind of limited region. Okay. If you can do that experimentally, then you can build a higher potential. Maybe it's easier, more difficult to tunnel. So that's basically the very simple idea. And then this is the localized doping can suppress the off current. Okay, so that is very important for leakage. Okay, so basically then we took this and do the calculation with the right doping, with the right gaps and so on. And then indeed what he found, that's exactly what he found. Okay, what he found is that if you dope in the middle, your potential is much higher. But this doping potential actually is a long range sort of electrostatic potential. So even though you only dope this region, actually potential leaks out. So you actually still have a wide width, but then you have a much higher potential. If you uniformly dope, you get this load potential, so you have larger tunneling. Okay, so basically you can easily tunnel through, and that one has more difficulty to tunnel through. Whether you N dope or P dope, it's the same kind of physics. So he calculates the doping, the leakage conductance as a function of where you dope it along a channel of 10, 11 nanometers. So if you dope in the middle, your conductance is much smaller. So actually you can suppress leakage current by a factor of 40 or so. So this is quite impressive, okay, for both N and P doping. If you uniformly dope the system like what we usually assume, then you get this tunneling conductance, which is much higher than this non-uniform doping. But if you doped in the wrong place, suppose you dope at the contact, then you are even worse. Okay, your leakage is much higher. So this says that maybe by controlling where you can put your dopant, not only you can control the variability of the device, okay, but also you can control the leakage current in the off state of a MOSFET. So this is kind of interesting, And so if you are interested in this, he published this paper last year, December, in Federal Letters. And let me look at another problem. I know that people here are interested in this new sort of two-dimensional materials called transition metal dichalcogenides. These are metal atoms with chalcogenides. And then so one of them is tungsten selenium 2. And these are layered system. And because they are layered, they are held together by weak forces. You can actually take a layer out of it, so you can make one layer. One layer is 3 atomic planes. Okay, this is one layer, another layer. So you can actually make a layer system, a 2D material, and which is like a graphene. Okay, and all of these structures, they all look like the same, actually. And then you have about, I think about 60 or so different kinds of this TMDC. From physics point of view, this TMDC has two very interesting property. One is that it has very large spin orbital coupling. Okay, so that gives you possibilities of doing spintronics. Another thing is that it has direct band gap of 1 point some electron volt, so which is very good. Direct band gap is very important. We know that for graphene, it's very difficult to create a band gap. And so it doesn't have a band gap, so we have to create it. Once you create it, you have to massage the graphene, and then certain properties change a little. And for this one, it comes with a direct band gap of visible range, so it's very nice. And so about 2 or 3 years ago, people have created this transistor out of this. But from my point of view, I was interested in two things. One is the spin orbital physics. The other is the valley physics. I'll explain a little. Okay, so we can use our software to simulate this emerging transistor, and that's what a student of mine has been doing. So this is the calculated band structure of this material, tungsten selenide, and you see that it has a direct band gap. I have a red and a black curve. This is splitting due to spin orbital interaction. Okay, so because this heavy atom tungsten, you have very large spin orbital coupling, which give you a splitting of about 400 MeV. So this is very large. So in this particular, let's look at spin orbital physics a little. So spin orbital physics means spin dotted on something. Okay, something is gradient of the potential cross momentum of the carrier of the electron. So gradient of potential is like an electric field. So basically this spin is due to electric field of the nuclei will feel a torque or feel a sort of action on the spin. So you can think about this rest to be an effective magnetic field, right? Spin is coupled to B, S times B. So this is a little bit like a magnetic field. So I can actually change effective magnetic field by changing this potential. So if you look at this material, the potential look like this. And then you have this, this is my layer. You have a dipole, you have another dipole. So you have a net dipole going from our left to the right. So you have a dipole field. Okay, E is along the plane. K is the momentum of the electron, which is in the plane as well. So you have two vectors, they are in the plane. When you cross product, you get a vector B, effective B, which is outside the plane. Right? So when you have an electric magnetic field which is pointing in the z direction, it tends to orient your spins in the z direction. Right? So basically your spin will be Zeeman-like spin, up and down, things like that. So in this actually material, you look at the spin, they will form 90 degrees to the plane. Okay, in a lot of places of the Brillouin zone. Okay, so or minus 90 degrees. So either have up or down spin, they point like that. And then in Brillouin zone, they are in K and K prime places. These are in the Brillouin zone. So these spins at the K are all spin up, at K prime all spin down. So K up and K prime in Brillouin zone, they are very far from each other. So they don't couple very much. So these are two valley index. So in this problem, I have two spin index plus two valley index. Okay, so that's very interesting. And you can have a valley physics in there. All right, and we calculate the spin, in K is all positive, in K prime is all negative, so spin up and down actually goes, it really looks like a Zeeman spin. Now, the important thing is that I can add an external electric field, maybe. So that will add a field here to give me another effective magnetic field. So I can tune the spin by external voltage. So that's the idea. So what I'm doing is to make a transistor that I put a gate voltage here, and then the gate field is perpendicular to the plane. My K is in the plane, so when you look at the K cross the field, the force is inside the plane. So basically, the external effective magnetic field tries to orient my spin from the z direction to the plane. So by adjusting the external voltage, I can actually change the spin texture of this system. Actually, I don't break time reversal symmetry, of course. Spin up go this way, spin down will go other way. You still maintain spin, So basically the physics is that if I have spin goes like that, inside this gated region, it will just change the direction. Okay. So when this changes direction, when he exits from the other side, the conductors will be tuned by whether this electron spin to be parallel to the outside spin or anti-parallel. You get a modulation of your electric current. So you can actually calculate this spin texture and whether it's 90 degrees or not 90 degrees. So you can see that this spin texture is really changing due to the external field. So we succeeded in changing the spin using an electric field. That is something that the spintronics people likes to have. Okay. So there are many other methods which does this, but it seems that in this material you can easily do this with a few, actually 5 volts of voltage. You already see it. I mean, even 1 volt you can already see it. So this seems to be a very large effect due to the large spin orbital coupling. And then your conductance will be modulated by the spin by gate voltage due to this spin precession, actually. So that is the physics that this material can give us. Now, as I said that I have 2 indices. I have a spin index, S. I have a valley index, tau. Okay, so basically my current, this is alpha is the left electrode or right electrode. So if I measure my current, I in principle will have 16 numbers, right? I have 4 by 4 matrix, so to speak. Okay. So it would be extremely interesting to break time reversal symmetry so that this tau and S are separate, and I can look at the the very large valley current. Okay. We know we have electric current due to charge. We have spin current due to spin. I might be able to create something called valley current that my electron goes through each valley, giving me a current, and then that will be separating the current in a K space. That's something cool, I think. And then we can calculate the current as a function of the gate voltage. You can see the transistor behavior. And then in this case, we already see a little, about 2% of the valley current. But because time reversal symmetry was preserved, I don't have a very large valley current. And then so my student, actually, he has added a circularly polarized light to break time reversal symmetry, and that should be able to create a very large valley current. And I don't know what physics we can actually dig out from there through this 16-element sort of electric current matrix. So this is very interesting material. It's emerging, and I can imagine many things happening. Okay, so this is transistor work. I want to spend the rest of my time, a little bit, about 5 minutes, to show that I'm a theoretical physicist. Okay, so I want to talk about this very tough problem of calculating device-to-device variability. So this problem was, I have a research grant from SRC, and when I go to these meetings, I meet these engineers from big firms. They always ask me whether I can do this. Calculate the variability. Not only calculate the average, that's what I told you, we can do average, but also what is the variance of the average as a function, of whatever. So if you look at experimental data for transistors, you create 1,000 transistors, their property, threshold voltage in this case, just scatters all over the place. So if each transistor behaves differently, it's kind of difficult to design a circuit. So people want to know, how do you control this variance? Especially when you get to very small transistors, like nanometers. But this is theoretically a very tough problem, because to calculate the variance, I have to calculate the transmission coefficient square average. As I told you that I learned how to do T average, right, through many years of work. Now we have to do a square. This is just really very tough. And this is a theoretical problem. And so essentially what we did is that we need to average 4 Green's functions. Because each T is 2 Green's functions. Now I have 2 T's multiplied together, and I have to average over 4 Green's functions, and with atomic potentials. This is just a unfortunate, tough problem. So we use a multiple scattering theory and Feynman diagrams to generate this very complicated vertex. So essentially, I use this multiple scattering theory. Green's function is written in terms of the scattering matrix, and in scattering matrix, I expand with like this, and then they can be represented by all those Feynman diagrams, and you have to sum up a subset of diagrams within the coherent potential approximation, and in the end you get some formula, okay, so which you can calculate. So I will not show you this diagram calculations, vertex. Okay, so in the end, we were able to calculate the average of t squared. Okay, and this allows me to calculate the variance of the measured quantity due to disorder effect. Edge roughness, grain boundaries, random directions of the grains, impurities, and so on, and that will give us capability of calculating the device-to-device variability, and thereby I hope to shed light on how do you create the material so that you have smaller variability, and that will give manufacturers more yields in their production. So this one we test on one-dimensional models, and our theory works perfect. One dimension I can solve exactly because I know exactly how many configurations. I evaluate exactly, and then we can find that our theory agrees perfectly with the exact solution. And so in the end, we were able to publish this paper, this technique, and then this is a calculation of a magnetic, metal with just a metal with some random, vacancies. And then you can calculate the transmission coefficient as a function of energy. Not only you get a curve, but you get a band. So the width of this is the variability that you calculate. So now I think we can predict device-to-device variability. And I have some students working on the threshold variability and all sorts of different variabilities in engineering issues. And so this is another sort of theoretical physics that found use in engineering discipline. So I don't want to bore you with a lot of details, but we have calculated a lot of other systems, such as molecular junctions, carbon electronics, topological insulators, and of course semiconductors, devices is the focus of our group. And we also work with industry on copper interconnects, and that's a very tough problem. In this computer I have maybe 25 miles of copper wires, and then these wires are 70 nanometer in line width, and then so there are a lot of resistance coming from the wires. That's why our computers are so hot. So the issue is that how do you reduce interconnect delay as well as the heat generated by the wires, because you have so many miles of wires. And so by doing this disorder scattering, we can understand where this resistivity comes from in these wires, and then can we use some barrier atom, some coating to reduce it. Okay, so these are issues that we can help out. Okay, and of course the most important thing that I think this research program will lead to is to work on emerging systems that where there is no experimental data, and then we can make quick evaluation of technology, and then point people to the right sort of engineering directions. So that's very important. So this is basically the last 10 years of my work, and that we solved this, several very tough problems. And so now what I believe that we can begin to predict device characteristics and device parameters from first principles without any parameter. And we are working with engineering people to actually parameterize the compact model now from just these principles, first principles. And so we have added other things. Electron phonon scattering, for example, is very important for devices like TFET, and also just simply for usual room temperature device operation is important. And we have non-collinear spin on spintronics, and I have a very large research program on magnetic tunnel junctions for MRAMs and so on. Professor Miao here has done some seminal work over there on MGO and on the interface impurity scattering, which reduces your tunnel magnification ratio. And so he and his previous supervisor did some very nice work that we actually followed up also on the theoretical side. Okay, and I have no time to talk to high frequency transport. There's a lot of theoretical physics there. When you have very high frequency, like 5 gigahertz, or so, that you have to worry about at this nanoscale, things like displacement current. We never worry about in solid state physics. You know, this induced current becomes very big, and that actually changes your characteristics. So at high frequency, there is another set of theoretical physics, and hopefully in the future that I will have time to tell you. And the transient, you know, my transient is better than yours because it's faster. So you have to calculate the speed, and this is actually a very tough problem as well. But we now know how to do this. We did them. And so I can see endless applications, okay? I have a real big handicap is that I was not trained as an engineer, so I would like to basically work with engineering people to find, you know, this sort of seminal important problem to solve. Okay, so yeah, so now we push this as well. Okay, so this is the research that I want to talk to you about, and that I think we can solve some nifty problems. Let me thank my funding. I got a lot of money from different agencies. We even get from NRC, IRAP, and also SRC. And I'm a member of a very large research center developing software from atomic all the way to circuit simulation. So we also get some funding, and I wish to acknowledge them. Thank you very much.
Thanks very much. Any questions?
Yeah.
Thank you very much for the talk. I enjoyed it. I have a general question.
Yeah.
Not necessarily. Let's say this is a piece of nanomaterial and I want to calculate electron scattering.
Yeah.
And it has like 10 silicon atoms, and I want to start, and similar to that, I add a few phosphorus atoms as doping. So when I run DFT, the band gap that I get is different because of adding phosphorus atoms.
Yeah.
So how should we resolve this? Like, because I'm confused. If I say, okay, without phosphorus atoms, I have real band gap. Then I start with this band structure and calculate the scattering, and phosphorus atoms are the scatterers. But if I add phosphorus atoms, the band gap is not the real one. It has been changed because of this. So how do you...
Okay, so let me answer this way. In real systems, you cannot put 5 phosphorus in 10 silicon, right? You can never dope it in. It's too big, this concentration. They just simply cannot. So usually in the real systems, you are talking about 10 to 19, 10 to 20s maybe if you push it. And this concentration is low enough, so the doping will change the potential mostly. Okay, the disorder scattering will not be very big in those cases, okay, because you dope 1 in 10,000 or something. So disorder, and then you may occasionally see some impurity bands or something. It will not really change your band structure. So, but if you make a theoretical model that I put 30 atoms, I put 5 impurities in there, I'm not really having a silicon anymore. This is a theoretical material which might, the chemistry changes so much, and you might get different band gaps, and then that will be reflected by your calculation, right? But if you, like we do this, we will see a doping potential and so on, your Fermi level is changed, and you have that kind of physics, but you don't see this narrowing of the band gap or something like that because of the impurity concentration. I think in your case, maybe you have put in so many impurities, you should not call your silicon anymore, okay? Something like that, I guess, okay? Yeah. Yeah.
So in NEGF-DFT self-consistent simulation, so you explained that after NEGF calculation, the charge density is changed, right? But that charge density affects DFT part, but at the same time, it also affects the electrostatic part.
Yes.
So then, where do you put your this Poisson equation loop?
Yes. So I have I just showed the loop. Rho I get H. But in order to get H, one of the steps is to solve electrostatics by solving Poisson equation. Okay. So H has many terms, right? It has kinetic energy, it has a Poisson solver, it has exchange correlation, and might be some other physics, being orbital, things like that. So one of the terms is your Hartree, which solves by Poisson equation. So we solve Poisson equation on real space grids, so we can put gates, different external potentials. Okay. Yeah, that's where it enters, yes. Yeah. So I really want to stress this. This NEGF is not a convenience. Like in the literature, you find people think this is Green's function, it's just more convenient. No, it's not a convenience, it's a necessity. Okay. Without non-equilibrium Green's function, you don't get non-equilibrium density matrix, you don't have the right non-equilibrium physics, and then it doesn't matter how accurate your Hamiltonian is, you get completely wrong. Okay, this physics is simply not there. Okay, so the Hamiltonian is important in the sense if you want to get accurate numbers. Okay, but if you are interested in general physics, you can do many other different kind of Hamiltonian and still publish beautiful papers. Okay, so it's not, we often do effective math, tight binding and so on. Okay, so this is not the critical thing. The critical thing is to realize the non-equilibrium statistical mechanics. And I think that's very important. That's why engineers can design all of these computers without any Hamiltonian. They solve Poisson equation, and they solve a Boltzmann equation. And that is where the physics is. So it's absolutely critical there, okay? And obviously that we would like to move on, from this sort of non-equilibrium to real non-equilibrium. In that case, you have to solve something called weak knot distribution, and quantum Boltzmann equation, all this complicated stuff that you can solve for, 10 atoms or something right now. But that will bring us to real far from equilibrium phenomena. But that is the direction that I think theoretical physics is moving, hopefully. Okay, yeah. Everything is crystal clear.
Well, I have one.
Yeah.
One of the significant applications in the energy area, and energy is of great interest at the moment, is how do you optimize the thermoelectric properties of a material?
Yeah.
And I wondered whether you've tried to address this.
Yes.
And, minimize the phonon transport, maximize the electrical transport.
Yeah. So Arthur's question is that in thermoelectrics, the merit of the merit is called ZT coefficient, which is a ratio between some Seebeck coefficient, which is proportional to electric conductivity divided by thermal conductivity. So you know that there is a law which says thermal conductivity is proportional to electric conductivity. So if you increase the numerator, you increase the denominator. So basically when you make a ratio, your ZT coefficient is equal to 1. So it's been equal to 1 for 50, 60 years or something. Always, people doesn't matter what you do, because of this ratio, you are dead. So the idea of nano is to make some structure which has very good electric conductance, but very bad phonon conductance. So that's, in nanosystem, you often can do that, because in nanosystem, you don't vibrate very well. So therefore, there are interesting structures that people make which try to maximize your conductivity of electric conductivity, and yet do not increase your thermal conductivity proportionally, like making the contact worse, make it very thin, and also using even interesting layer material, like bismuth selenide was a thermoelectric material, but if you make it very thin, somehow it has a large ZT coefficient, like 4, which is very impressive. I don't know whether those kind of calculations are correct, but basically the idea is to make nanostructures which does not conduct phonon very well. Okay, so I talk about electric conductance. You can write down the same kind of non-equilibrium Green's function for phonons. Okay. And I have some students doing exactly that. And then you can couple the two. You can have thermal conductance and electric conductance in the same formalism. And that whole thing done by non-equilibrium Green's function, that's possible. But I think the idea is basically try to create nanostructures which does not conduct phonon very well, but at the same time has a good electric conductivity. That's probably is the way to go. But so far, it's kind of difficult. So in physics, people wandered into something called spin, thermoelectric effect, spin caramel, what is this words, spin thermal effect and so on. In that case, you can have some interesting phenomena related to spin-related thermal effects. Okay, so this is it's a very wide. This is a very difficult problem, because since 30s, I think people have reached z equal to 0.6 or something, or now we are 1. It takes many years, it seems, to make some progress. But I did see some papers on bismuth selenide. They got ZT equal to 4. I think maybe people know this here. I mean, I think ZT equal to 4 is the goal or something. Yeah, and so I think there are room for that. Yeah. So we also do a little work there, but I don't like thermal electricity, thermal conductance. So I basically focus on electric conductance over there. But you are right. This is a out open problem. Thank you very much.
If not, please join me in thanking Professor Guo for not only an excellent talk, but one that's understandable to non-theoreticians.
Thank you.